This is some information on moving horizon estimation. It's an approach to align a model with a series of measurements from a dynamic system. So if we have, for example, a measured input P, and then we put that same thing into a model of a system, so this is an actual system that we're trying to align to, and then we get some measured outputs, and that'll be Y, YM. And then we also have some simulated outputs, and we'll just call that Y. And so if we want to try to align these two, we set up an optimization problem called moving horizon estimation, where we have this alignment between the measurements and the model values. So we're trying to minimize the deviation between those two. We can have, for example, a 1 norm, a 2 norm, infinity norm, anything here, so n equals 1, and so for that case you have the absolute value of ym minus y. If n equals 2, that's a 2 norm, and ym minus y squared, and then take the square root. So every point in the horizon, we're going to take that difference between the model and measured value and square it, and then take the square root. A lot of times we also just do ym minus y squared. Okay, so for a squared error, if it's n equals infinity, that's the infinity norm, and that is to minimize the max of ym minus y. Okay, so we want to minimize whatever point along the horizon has a maximum deviation. We want to minimize that. Okay, but we're subject to these constraints. So this contains differential, okay, or these outputs y, inputs p, and these are equality constraints, and then also inequality constraints. We can have either one in this formulation. It's a very general form. We can solve everything from flight dynamics, estimating aircraft dynamics, to solid oxide fuel cells, to drilling in oil and gas. There's just countless number of applications that can be fit into this general framework. Okay, so in the overview of the class right now, the course, we are talking about dynamic estimation, in particular moving horizon estimation. There are other approaches as well. The Kalman filter is another one. Okay, so moving horizon estimation, if you have a under certain simplifying assumptions, moving horizon estimation will be equal to the Kalman filter. So if you get rid of any constraints on variables, if you set the horizon equal to 1, use the squared error, and there's a couple other simplifying assumptions, and it should give the same result as the Kalman filter. Okay, so if we look at horizon, we're used to seeing this, and maybe we're more familiar with, for example, model predictive control. Okay, in model predictive control, we're looking into the future with our predictive model, and we're trying to hold to this trajectory. Okay, and then we have a predicted output, and then we have manipulated variable moves that at discrete time points in the future horizon are trying to drive these points to the this trajectory. Okay, now moving horizon estimation then goes backward in time. Okay, so moving horizon estimation, we may have measurements, okay, going back, and then we may have unknown parameters. Okay, unknown parameters or initial conditions for these states. So I'm just going to write those here, and so the parameters can make the predictions move up or down, but we're going to adjust those parameters of our model to try to get the best agreement between the measured and the model values. So that's why we had the ym minus y, and we'll have that here, 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 and then at the current time. Okay, we're trying to align that, so we'll sum up all the differences and try to minimize those. By adjusting the parameters, or states, initial conditions of our model. Okay, so that's moving horizon estimation, and it's kind of analogous to model predictive control. But throughout these cycles, we're going to get new measurements that arrive, and before we do the forward prediction, we want to correct our model based on this new information that's available using this Bayesian approach for estimation. Okay, so that's so let's go and just do a couple. Let's just go do a couple examples here. Okay, so I'm just going to open up. Actually, let me go back there. I'll just go to that link. We have this online course for moving horizon estimation examples. Also, if you want to get to it, just go to APMonitor.com/DO for dynamic optimization. And then if you come down here to estimation, you'll see this one on moving horizon estimation. Okay, so those are the examples that we're going to be working through. This is the exercise. We're going to design an estimator to predict an unknown parameter and state variable. So we'll develop a model of the reactor and implement the model with moving horizon estimation. We'll do it in MATLAB, Python, and actually we'll do it in Simulink as well. So if you're going to be doing this yourself, I just recommend a few hours to work through it. I've also posted the solutions right down here, so if you need some help as you work through it, you've got the solutions in MATLAB, Python, and Simulink. Okay, so we have this reactor, and we have the feed coming in. The thing that we can adjust is this cooling temperature, TC. And it's an exothermic reaction, A goes to B. This is an academic problem used in many benchmarks in chemical engineering journals. Okay, and then we have the concentration of A. That's our species A, the reactant. It's going to be converted to B. And then we also have the temperature of our reactor. And it's going to be well mixed in here, so everywhere it's going to be the same concentration of A and temperature, and that's also going to be equal to what's leaving. Okay, we want to try to convert as much of this A to B as possible. And so we want to design, first of all, an estimator to predict the concentration of A leaving the reactor and the heat transfer coefficient. So that's how well the heat is able to conduct from the reactor to the cooling jacket. And we're going to try to estimate UA and the concentration of A just from the reactor temperature and the jacket temperature. Okay, and if you want to see more about this model, you can come here. Many more examples. It talks about the model, number of simulators in Simulink, linearization if you want a transfer function form, or nonlinear S function. Okay, but we're going to do this. So what I'm going to do is just go ahead and work through this one in MATLAB first of all. Okay, I'll just kind of explain what's going on with this moving horizon estimation, and the other scripts will be similar. I want to spend a little bit of time on Simulink as well, just to show what's going on with Simulink. Okay, so I'm going to go ahead and open up this reactor model. Also open up the moving horizon estimation model. This is in the APMonitor modeling language, so you can see parameters, variables, equations. Okay, so we have two equations. This first one, okay, right here, that's just a species balance. The second one, that's an energy balance. So this first one's predicting concentration of A, and this one's predicting the temperature. Now the rest of this down here, these are just some plot files, and you don't necessarily need to do anything with this. This is just some extra interface work. Okay, I just made a little schematic of the reactor on the web page. Okay, but that's our model that we had. The thing that you really need to pay attention to is are these parameters, variables, and equations. Okay, and then I'm going to come back here to MATLAB, and let me just go ahead and walk through this in debug mode. So I'm going to go ahead and run this, and just go ahead and step through it, And then let's look at, I'll move this over to this side, and let me move this one over here. Okay, and then I just want to take a look at some of my workspace as I go. Okay, so let me make that just a little bit bigger, and I'll just go ahead and step through this. Okay, step through. I'm going to create 2 new applications. Because I just clicked run. Okay, I was going to step through it, but I just clicked continue. It looks like. So this is what it's going to do as it goes. Let's just go ahead and check out the plot here, and this will come up with a plot of TC. Okay, so that's our cooling jacket temperature, and then we're also going to have the temperature of the reactor. Now you can see that there was initially some deviation between the two, but then it's going to be adjusting this UA parameter. That's our the UA is going to be our heat transfer coefficient as we in this reactor. Okay, so it started out at 100,000, and you can see that as it goes forward, it's going to converge to this is going to converge to the correct answer, which is about 50,000. Okay, so there it goes. It's going about to 50,000. Hit escape to just get out of that view. Okay, and then let's just look at our temperature again, see how it's doing. Okay, so if I come over here to temperature, hopefully that will bring up the plot. There it goes. Okay, so it's tracking the temperature very well now. I'll go ahead and make that just a little bit bigger. Again, my initial guess on temperature was off, and so it was able to adjust UA to get it to match. Okay, the other thing we wanted to do is predict the concentration of A as well. So concentration of A, that's going to be concentration inside the reactor, and here we don't have a measurement, which is a pure prediction. Okay, but in our script we had another version of the model that was running, and if we come over here to the MATLAB interface, okay, so this ran I think a total of about 50 cycles, and you can see for each one there was an estimated concentration of A and then a measured, or actual, not measured. We didn't have a measurement for this, so it's trying to align the two. You can see them converging, and then also the UA values. Okay, they're going to converge to 50,000. But let's go ahead and take a look at the plot, and then I'll walk through the script just a little bit more. Okay, so I just had scheduled a jacket temperature increase from 280 to 300, and you can see here is the measured reactor temperature. Okay, so as I went up in jacket temperature, the reactor temperature also increased, okay, but a little bit more slowly than the step change. You can see the actual heat transfer coefficient right here, and then here's the predicted heat transfer coefficient, so it converges to that value of 50,000. You can see also here the concentration of A. Now we are purely predicting this by trying to align this model and measured value here for the temperature by adjusting this UA value. And you can see that the two come together and track very well on the UA. Okay, so let's go through the script in just a little bit more detail. So I had the 2 applications. This was my plant. It had a different UA value and starting conditions in my moving horizon estimation. And then I called this function to initialize the simulation, and this function to initialize the moving horizon estimation. Okay, I wanted to run for 50 cycles. I just arbitrarily scheduled cooling jacket temperature. This is just for plotting for later, setting up the time. Each time step is 0.1 minutes. Okay, and then these are the cycles. Okay, so this is how I simulate my process. I just insert in line 30 the cooling jacket temperature, and then I solve it. Okay, just solve it for that 0.1 minutes, and then I retrieve the measured concentration of A, and the temperature. Okay, so that's my measurement. This is my simulator for my process, and that has different parameters than my estimator, but my estimator is trying to discover those. Okay, and then I have my measurement for cooling jacket temperature and then also for my reactor temperature, but I don't input my concentration of A measurement. Okay, then I solve my moving horizon estimation, and the rest of this is just to check and see if the solution was successful. If it was, then I record my UA, concentration of A, and temperature from moving horizon estimation, and that's just for plotting for later. Okay, now if it wasn't successful, okay, then I'm going to display the output of the solver. That may help me debug, and I just say, let's set those to 0. I didn't have any failures as it went through, and I just displayed that line for the MHE results. Just on the first cycle, I opened up that web viewer as well. Okay, and then here I just plot the results for subplots. There's the cooling jacket temperature. Here is my UA values, and then temperatures, and then concentration of A. Okay, so I'm just going to leave this open and then show the Python right next to it, and then we'll jump right into the Simulink as well. Okay, so I'm going to come back here to my, okay, I'll grab the Python. Okay, so go ahead and save that, and let me come back to the desktop. Make sure you extract these before you try to use them. Some people try to use it through the zip file. It doesn't work too well sometimes. Use it from the zip file, so make sure you extract those. Okay, so I've got the two files. Now I have my initialization of moving horizon estimation and simulation, where I just load my models and set some of the options. I'll go through some of these. They're very similar for the MATLAB, and so let's just do the simulation one first. Okay, so these are going to be very similar between the two. I'm just going to add my library. I'll clear any previous application. This one is just to load the model, load the data file, and then I'm going to set up these, classify these variables. FVs are fixed values over the time horizon, so just one value of UA over all of the time points, versus an MV, that's a manipulated variable. I'm going to have the status off, so I'm not going to try to predict that. I just want to measure it. So I'll have some cooling jacket temperatures that I'm going to be feeding in. Those will vary at every time point. I just have two that I'm trying to predict: concentration of A and temperature. Now this is just for the simulator. So I have it in I mode equal to 4, that's simulation mode. I just set the collocation nodes to 3. I'm solving it with the IPOP solver, and then I'm just telling it that the cooling jacket temperature is measured. So use that in the simulation, and then return simulator initialize. Now the same thing is happening here, where I am loading my model files, classifying my variables, set a few options, and then actually let me go down to the simulator. Okay, so this is the one that's similar to the init sim. Load model, classify the variables, set some options, and then turn on the measurement. Okay, so same thing on, let me go back to the MATLAB version. Let me initialize, so let me spend just a little bit of time on this, discussing some of the options for the moving horizon estimator. Okay, and that one is right up here in the Python. Okay, so I'm going to clear the application. I'll load the model and the data file. Now this version of the model has different parameter for UA and different starting conditions for my CA and temperature. Okay, I'm going to try to estimate those. And then I'm going to load, classify my variables. Again, UA is just constant over the horizon. Cooling jacket temperature can vary at every time point. Now for a model predictive controller, this one I turn the status on to have it manipulate the jacket temperature, so I can control the temperature in the reactor. But for in this case, I'm going to have the status off for this because I'm looking backward in time and I just have measured values for the cooling jacket temperature. But this one has the status it's on. That's the one that I'm going to try to estimate, and I have no measurement for that. I also set some lower and upper bounds. Okay, and then this one also I had a measurement available, and the temperature I also had a measurement available. I didn't have a measurement available for a concentration of A. Also, I set a measurement gap. That just allows it to, if there's noise in the temperature measurement, that it won't try to fit to the noise. So that's just a dead band. So as long as my model prediction is within 0.1 of the measured value, then it doesn't try to adjust the parameters of the model. Okay, and then this is the area that I explained previously for the MATLAB. Okay, just server, 2 different application names, initialize the simulator, initialize the moving horizon estimation, 50 cycles, and again, this is going to be very similar. Here I'm just going to declare some storage matrices, set up time for my plotting. There's one thing you need to do in Python you don't have to do in MATLAB. You got to allocate the storage before you go into this loop. I'm going to go 0 to 50 cycles, and then this is just the process simulation. Okay, then this is the estimator right here. I'm going to print that line just like I did in the MATLAB script. Okay, and then the rest of it is just going to be the plotting. Okay, so let me come down. So I just plot with matplotlib. Now I think this it's kind of interesting when just the comparison between the two. I really like the way the plots in Python look. I think that's a really nice feature of the Python. Okay, so it's going to open up the web viewer as well. But let's just watch this as it tracks. We're going to see the UA value. Pay attention to the UA value on the right. The actual value is 50,000, and I have estimated values that you can see they're going to converge to 50,000. Okay, so I'm just going to go ahead and close that. We're going to go over to the Simulink, in fact. It gives the same results as the MATLAB version. Okay, so let me come back over here and let's get the Simulink one now. Okay, so Simulink is very similar to MATLAB. It's going to use scripts that are almost the same as MATLAB. Let's see. Let's see if I can grab this one again. Okay, so that has downloaded, and it looks like there it is. Okay, so this was just a partial one. Let me extract this one. Okay, and let's go over. Going to open up the CSTR MHE. That'll be the Simulink one. Okay, so let me see if I can open this. It's a little bit slow on this tablet computer. It should hopefully be a little faster on your computer. Okay, and it looks like it's way over here on the side. Okay. Okay, so this is my moving horizon estimation. I have this is in the middle right here. That is my, actually let me just go ahead and grab this and I'll go ahead and mark it up a little bit just to explain the flow of the data. Okay, I'll paste it in here. And I'll make this just a little bit bigger just so we can walk through it. And okay, so what we have here is a jacket temperature. I'm just going to step this from 280 to 300, and I think that happens at 2 seconds or 2 minutes of simulation time. Okay, and then I'm just going to hold all of these constant. The moving horizon estimator isn't planning on those changing, but you could change them and have a little bit of model mismatch. You really don't need this temperature set point right here. That's just if you wanted to develop a controller. Here's your plant simulator. Now I did this one as a reactor S function, so that uses a MATLAB integrator. But I'm having all of these come in to that, and then it's going to then predict the temperature and the concentration. Okay, and then what I have then is a moving horizon estimation. So it's going to feed in not the concentration and the temperature, just the measured temperature and also the jacket temperature. So it's going to feed those in to the moving horizon estimator. Now this pulse right here, that tells it to go every 0.1, actually I keep writing seconds, but it's actually minutes. Okay, minutes. And then it's going to execute this moving horizon estimation. And then what comes out is going to be a concentration of A predicted. Okay, and then also a UA predicted as well. Okay, and then I'm going to compare it with the correct UA value. We're also going to be able to see the reactor temperature and concentration right here, just as it's executing. Okay, so let's dig in just a little bit to this moving horizon estimation block. So we're implementing moving horizon estimation within Simulink. And so what I want to do is just go ahead and go back here. Go ahead and close this. And when I open this, I have an interpreted MATLAB function. And if I open that, this is just my MHE call. So this is very, very similar to what I just showed you, but it's just had to write it as a function. And then I had to have some persistent variables just so the first time through it would set up the problem and call this initialization script. But then the rest of the time through, I'm just inputting my measurements from this, the simulation. I solve the moving horizon estimation, and this is just processing the results and seeing if it's a good solution. Now here I tried to solve it with the APOP solver. If it didn't solve successfully, then I switched to the IPOP solver and solved it, and then just retrieved the values here. And then I output this back from the block. I display this at the command prompt, and the first cycle I'm just opening up a web viewer. And then I return. So this is the custom function that I implemented here in the Simulink block. Okay, so let me go back to the Simulink block. Okay, so this is just the custom function that was implemented here in the moving horizon estimator. So let me go ahead and run this for 10 minutes of simulation time. Okay, so when I run it, it's going to go ahead and compile. Okay, oh, you know what? If you get that error, it means you're not in the correct directory for your MATLAB. So I was here in this directory, and I need to go into this other directory. Okay, let me just go ahead and double click that. Okay, so I'm in this directory now. So just make sure you're in the correct directory before you execute, and you hopefully won't get that error. Okay, so now it's running. It opened up the web viewer. I'm just going to close those. But you can see the temperature and the reactor concentration here in the upper right. The thing that we want to go to are these, these plots. We can see the temperature. We can also see the UA value. Let me go ahead and just scale that. There it goes. Okay, so you can see it estimating the UA value. Somehow that doesn't want to go full screen on me. And then it's also estimating this this concentration. Okay. Okay, so that it looks like. Okay, so here's some results. This is a tablet computer. Hopefully on your other computer it'll be a little bit more horsepower and run a little bit faster. But here was some of the results just that it plotted at the end. But if I come to this concentration, I can see that it was able to start estimating and had very good agreement. And then if I come to the UA value, you can see that it very quickly went to 100,000 initially and then very quickly converged to 50,000. Okay, so that concludes, I'll go ahead and close this down. That concludes this tutorial demonstration on moving horizon estimation. Again, what we were doing is using this prediction and actual system and comparing the two, and then these were our model equations. Okay, subject to those model equations, in this case a species balance and an energy balance, and we're going to be adjusting the parameters of our model and the initial states in order to be able to align the simulated output with the measured output.